Okay, hello everyone. This is the continuation of last sections, which is the polynomials, and we are going to continue our topics on quadratic function. And if you remember, we have learned or studied the polynomial until the maximum minimum value for quadratic functions. Okay, but so before we go through what's next, I will go to review what we have, at least to see how we can make out the maximum minimum value from our standard operations on the quadratic functions. Okay, now if we see the quadratic function, for example, if we see the functions, it's negative x squared plus x plus 2. Now we could have at least two perspectives. Okay? The first is we take these functions to be standard form, so we are going to complete standard. So we are going to express the function in standard form. So how do we do that? Is first we need to make it clear for the variables and the constant. So we at least we kind of separate the variables and constants. Okay. And then we are going to add with a constant that completely make the variables has a square. So we are going to have, so x squared minus x, so we are going to take the constant on here, this is 1, take by 2 and then square, so we have 1 over 4. So 1 over 4 will be written here, or let me write with red. So plus 4 plus 1 over 4, and then we need to plus 2, and then we are going to minus with this minus with this negative 1 over 4. So minus 1 over 4. Okay, and we can simplify this, becomes x minus half squared, and then plus this become 8 over 4 plus 1 over 4 is 9 over 4. So this is our new expression for a function. So we are going to have the center will be on half and 9 over 4. This will be the center. Or we could say it has a max value at x equal 1 over 2, or we could also say that the max value, or maybe max value at x equal half is 9 over 4. Okay, or if you would like to see the graph, is going to be at least going to take this is 0, this is, let's say, 1, so this is half here, and this is 1, this is 2, a little bit here, then we go by okay, and then this will be 2 around, maybe a little bit going over there, okay, and over here, and make it longer there, This is -1, this is 2. Okay. And this is the maximum value, which is the half, and 9/4. Yeah, more or less this is how it looks like. And we could also just look at the functions, the original functions. We have this, right? And we know that from the last sections here, that we could say that this will be our vertex, negative b over 2a. So we're going to have negative b over 2a, which is the negative 1. So it's 1 over 2. Oh, this is plus, sorry, plus. So so the vertex is negative b over 2a, which is half, and the max value is f half, and we can take that, and we know the answer is 9/4. Okay. Okay. So let's say we have another example. Let's say x squared plus sorry. Let's say we have x squared plus 4x, and we have another functions, negative 2x squared plus 4x minus 5. The first one, we could take factorizations, so x plus 4, like that, and we know that, or we could just directly use the negative b over 2a. So negative b over 2a, negative 4, 2, negative 2. So x, negative 2 is vertex. So minimum value is 4 plus negative 8, negative 4. Okay. And how do we know it's minimum or maximum? It's from this. Okay. If this is positive, then it will be minimum value. Or if you would like to know how this works, is just imagine the typical function of the x squared. Okay, this is x squared, right? It's x squared positive, okay, and it's going to have this minimum, right? Okay, that's how the minimum maximum value works. Okay, now next is the other function. This is function g. So we also say that the vertex will be negative 4 over negative 2, which is 2, like that. Let me write here negative b over 2a. So this will be 1. Okay, so that is our vertex. So at f1, that will be our max value. So it's going to be negative 3. Okay. So that is the quadratic functions and how to observe or to identify its maximum and minimum value. Okay. Okay, the next part is we are going to discuss more about the polynomial function and its graph. But before we are going to take some time to work on that, let me write first the title. So polynomial functions. Okay. So first is, let me give you the terminology just here. Okay. So some terminology, and this is for all kind of polynomial. So any polynomial will be going to be having this general form, this px. Usually we say with px, p is for polynomial, and we have this constant, and we have this variable x, okay, and then which we have for every degree that can be possible in these terms. So we have the coefficients, we have the constant term, leading coefficient, leading term. Actually, it's not really going to necessarily to be memorized, but it's good if you know at least this general term, okay? And the an is not equal to 0, okay? So we are going to have, for example, if we have 3x with power of 5 plus so this is our leading term, okay, leading term, okay, leading term. This is leading term, and it's the polynomial is degree 5, the highest degree of the polynomial, okay. And this will be the constant term, okay. And then the other part is, I think, not really important, okay. So as long as you know which one is the leading term and the constant term, you can define your polynomials, okay. And for example, if we look at another example, this is how it looks like. So we have examples for degree 1, 2, 3, 4, and we have this leading term and constant term, okay. I think not really a big deal, so you should be familiar with this, okay. Another example is for the some basic of monomials. Monomials means it's only having one coefficient. So y equal x, y equal x squared, y equal x cubed. It's called a monomial. It's only have one terms. So this is some of the graphs of the monomials. And of course, since we have learned about transformations, we could also transform all these monomials with the transformation property that we have in previous chapters, okay. Oh, sorry, not this. Okay, so if we would like to like, for example, we have negative x cubed, it means that we are going to take this positive, okay, and then mirror with the y-axis, and it goes to be like this, okay. And the same way, if we have x minus 2 with power of 4, which means we are going to look at this x with power of 4, and then we take, because it's negative, we take to the right 2 units. 2 units to right, and this mirror at y-axis, okay. And another part is this negative 2x power of 5 plus 4. So we take this upwards 4 units and multiply with 2 and with negative also. So if we take x5 as this, so we take the mirror, so mirror y-axis, and then we multiply by 2 by a factor of 2. Okay, and this is just some preview from the previous part, and I hope you still remember how to do the transformations. Okay, next is we are going to see the AND behavior. So polynomial functions will be having smooth and continuous if you look at the functions, while if you take a look at the two first graphs, this part, okay, this one, you will see that the first one it has discontinuity at some point, and in the second one we have a point that where x it's having a sharp corner or a cusp. It tends to be not a polynomial. Okay, so the first two is not a polynomial function. So if you remember, degree 0 or 1 for polynomials, it lead to line graphs, and from degree 2, 3 and more, it will be a curvy, or a parabola. Curvy has a curve, right? So it means that this is the at least degree 2. Okay, and this part here that has like a similar to line, it has combination of line equations with a curve equations, and we don't really can say it's a polynomial, but it's part of polynomials. Like this part here is like polynomial, but if we look the whole thing, the general graph, it's not a polynomial because it has this line equations. And it is also true for this part. We have a discontinuity here, which is not in a polynomial behavior. Okay. And the end behavior is we are going to look at the when x going to larger numbers, and x can also go into negatively large. It means going to the opposite direction, to the left. Okay. So this is x increase without a bound. We can say x increase negatively, or we can say decrease because it's going to the left. Okay. And we can also describe the behavior as through the degree of the polynomial itself. Okay? So when we have the polynomial odd degree, we could see that when x is going to infinity, this part here, y is also going to infinity. And when x is going to negative infinity, dy also negative infinity. Okay. This is when the leading is positive. When the leading is negative, we are going to see the opposite sides. Okay, opposite. Okay, the opposite. So I believe you could work this out with the x cubed and x squared. Okay. Okay, I think not a problem here, okay, as long as you can make sure that you are able to identify your functions. Okay, yeah, so you can take a look how they going to behave. Okay, okay, I think this is clear, pretty clear, not really necessary to memorize everything. Okay, I think it's important to remember how the x cube and x squared looks like. Okay, I think that will be a better examples to describe all this odd degree and even degree. Okay. Okay, the next section is how we are going to take times to draw or to sketch the graphs from these polynomials. Okay, so let's do that. So we could start from real zeros of polynomials. So if let me start with the definition. So if P is polynomial functions, then C is called zero of P if P of C is equal 0. Okay. So let me write, if P is polynomial, this is a theorem, and C is real number, then the following are equivalent. C is a 0 of P, and then x equals C is a solution of P of x equals 0. 3x minus C is a factor of Px, and C is the x intercept of graph of P. Okay, so this 4 is actually the same thing. So we could take this 0 to graph our function. So we are going to get the x-intercept, because we are going to equaling the functions with 0, and we can solve the functions and find the solutions, and that solution will be the intercept for x. Okay. So for example, we take the functions x squared plus x minus 6, and of course we have learned how to factorize, and here is the one of the application for the factorization. So we could take this, becomes x minus 2 and x plus 3. So the one that makes 0, so we need to make it a 0. So we need to find which x that make this equation 0, which we get the x is 2 and x is negative 3. It's our 0. Okay. So if we look at the x equal 2, so 2 is the 0 of P, x equal 2 is a solution of Px, okay, and x minus 2 is a factor of Px, and 2 is intercept of graph P. Or you could write two of them, like 2 and -3, we could say like that. Okay. So you could imagine the graph. So at least you know that this will be having -3 and this will be having 2. And the graph will be crossing this 2, okay? Maybe like that, okay? Around like that. Okay, that's how roughly the graph will be. Okay, now we are going to look at the one theorem that is, I think, important in polynomials, and it's really applicable. It's called the intermediate value theorem. Okay. Let me go through the theorem. So the theorem says that if P is a polynomial functions and P of A and P of B have opposite signs, then there exists at least one value C between A and B for which P of C is equal to 0. So this is theorem for proving that there is at least one solution at this polynomial, that when you plug in some numbers A or B, you will see that A is a positive opposite of P of B. So if PA positive, maybe P of B will be negative. So we will have something in between that is 0. If we look how it is in this graph, okay. So this is just an example. Okay, A and B can be any numbers, but if in our example here, if A is here and P of A is here, which is in the negative, right? In the negative y, right? And B is here. P of B is PA. PB is positive, right? So we know that P of A is negative, P of B is positive, but these curves need to be connected, right? So it should go through the x-axis. So it needs to cross x-axis, right? Which means it should have C. Okay, it should have C, and P of C is 0. Okay, so whenever you find the well, let's say you find some functions, polynomial functions, but and it seems that it's just asking that whether they are having zeros or having the roots or not. You could prove that through this theorem. So you could take some numbers and then you need to just look at the numbers and then plug in the numbers, look at the value, and when you see any opposite signs, it is clear and obvious that the polynomials functions will have zeros. Okay, at least one zeros. Okay, at least one. Okay, that's the intermediate value theorem for polynomials. Okay. Okay, let me give you example on how to sketch. Okay, using zeros to graph a polynomial function. So let's say we have P of x let me just give you the already factorized, so we don't need to factor again. So here we get the zeros from this px. Our x equal -2, 1, and 3. Okay. So we are going to determine the interval. Also, let's write with the 9 number as usual. Okay, so we could take this -2, 1, and 3. Okay. And then taking some numbers from the left part, we could take -3. So negative, negative, negative. So plus and negative, it's negative. Okay. So negative here, and then between -2 and 1, we could take 0. 0 will be negative, negative, so it's positive. Okay. I think it can go a little bit higher. Okay. And then between 1 and 3, maybe we could take 2. 2 is positive, positive, negative, so it's negative, right? And then after greater than 3, we could take 4. 4 is positive, 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 so it's positive. Okay. So which means negative is below x-axis, right? Positive means above x-axis. This is below x-axis and above x-axis. Okay, so negative, positive will determine which region the graph will be. Okay. And then we could also take the table to make our exact coordinate. So we could take x and p of x. We could start x from -3, -2, -1, 0, 1, 2, 3, 4. This is if you want to sketch the graph exactly on some coordinates, and we can connect all the coordinates all together in one curve, and we can match them with our signs here, with signs that below of x-axis and above x-axis. Okay, so we could take this -3 and multiply it all together. This will be going to be 24. -2 is 0, right? So this is the zeros, right? The zeros. This is also zeros. This is also zeros. This is 0, 0, and -1, -2, -4. So -1, -2 is 8, right? And we have 0, -2, -6, plus, so it's +6. 2 will be -4, and 4 will be 6, 3, 18, right? 18, right? Okay, so we have all this points. Okay, and then we could take these points and write down on our graphs. Okay, so we could take 1, okay, so we start from, let's say, just to note the zeros first. So we will have -2, 1, and 3. So all this will be zeros. And before we go through, or let me start, I think we can start from here, from the left part. So -2, or maybe start with -3. -3 is going to have down there. Let me use the green color. So it goes to crossing -2 like that. And then in between we have -1 is 8, so it's going to let me erase a little bit and make it more clear. So it's going to maybe around here. That's the 1, and then after -1 is 0, it's 6, so 0 is 6, so maybe going through here, okay, and then 1 is 0, so we are going to get through all of that. Maybe make it more clear. 1, and then 2 is -4, maybe here, okay. And then 3 is 0, okay, and then 4 is 18, so 18 I will go straight up all the way there. Okay, so you will see that it's true that we have this is negative, this is positive, right? So we could match all this below and above from the signs, and from the test point we could also match the coordinates exactly, but I just give roughly coordinates because it has really big -24 and 18, so it goes to -24 here and 18 here. Okay, so at least we can make a graph from the polynomials. Okay, we can have the signs identification for make sure that the graph is on the negative region or positive region. Okay, I think that's clear. Okay, maybe another examples. Let the px is x cubed So first is find zeros of P, and the second is sketch graph of P. Okay. Now first we need to find zeros. So for A, so find zeros, we could factorize first and make it the equation becomes like that. We could factorize one more time. So we could simply conclude that the zeros are x equals 0, x equals 3, and x is -1. So we could say the x-intercept is 0, x equals 3, x -1. And y-intercept is p of 0, and this will be 0. Okay. We could also make a table of x and p of x, or we could take the line number first here. So we could take from -1, 0, and 3. So we could take -2, -2, -5 is positive, and negative is negative. So negative, and between 0 and -1 we can take -half. So -half, negative, -half, positive, negative, positive, positive. Okay, positive. And then we take 1. 1 is positive. Let me erase this. So 1 is positive, negative, positive. So it goes to be negative. It goes to be negative, and we take 4. 4 is positive. Okay. So we know how the region will be, which one is positive and negative. We can also take the point. We could take the from -2, let's say -2, -1, 0, 1, 2, 3, 4. Okay. -2, we could take -2. It's 10 multiplied with negative, it's -10. -1 is our 0. 3 -1, 0 is 0. Because this has two zeros, we need to make another points. So we could take -12 as we assume from the line number. So -12. So -12. So 6/2, 7/2, 3/2, 10/2. Multiply with another half. It's 7/8. 7/8. 0, 1, 1 is -4. 2 is -1, -2, -6. 3 is 0. 4 multiplied by 5, it's 20. Okay, so this is all the points that we need. So again, we need to draw the graph. Okay, so we could write all the necessary zeros. Okay, and we will start from the negative region, from the left here, right? From the negative. -1 or -2 is -10. So we are going to take this -2. Maybe 10 is around here. So we are going to take this and crossing this -1. Okay. And then we have half. -half is 7/8. So let's say this is 1 is there. And goes down. Okay, goes down, goes to the 0 again, and goes to the negative signs. So 1 is -4, so it's going to be around here. Go there. 2 is -6. -6 is maybe around here. And then goes up and takes zeros like that. And then 4 is around 20, so it goes there, 20. Maybe just make it clear that it goes up like that. Okay. So we could see also from here, as x is going to -infinity, y is going to -infinity. As x is going to infinity, y is going to infinity. Okay, and it's true because we are going to have the odd number here, the odd degree. We have the odd degree. Okay, right? Okay. So that's how we can sketch the graph through the zeros. Okay, through the zeros and the line numbers to find which region the graph will be. Okay, now we are going to continue. If we look at the last examples we did, and if we remember how the maximum or minimum value that we have on the quadratic functions, it also have, we can also see that the polynomials also have its own maximum and minimum value. But how can we say this point, let's say, and this point, is it maximum or minimum? If we remember from the previous part on the quadratic functions, we only have this graph and we say this is minimum because we know that it's the lowest point, right? and we have this, and we say this is maximum, and we call the maximum because it's the highest point. But how about if we have something similar, they behave perfectly similar, but it is in between of the graph, or we have one curve and it has its own minimum and maximum somehow, but it's not the highest or lowest point. So we call them, okay, we call them this part here as local, okay, local max and local min. Okay, so we will have the same property, the same behavior, but we are going to make them maximum or minimum locally. Okay, because clearly the highest point and the lowest point is clearly on this side, right? On the end points, right? Right now, let me give you the details. So we could say that this is, we call the extrema, or the extreme, local extrema. Okay. So if we see something like the previous example, we could say that if we have this A, it's called the local maximum point, and this B is the local minimum point. Okay. Okay, that's some additional informations. Okay, so we know that we will have the maximum and minimum, but we say that we are going to have the local one. Okay, and the theorem says that if the P is a polynomial degree of some n, so the extrema will be n minus 1. So if we have, let's say we start from x squared, okay? So if degree 2, then extrema is 1. And it's true, right? It's true. If we have degree 2 like quadratic function, we can have only 1, right? And if it's degree 3, like the previous one, we can have like this. So we have 2, right? And if we have 4, like for example like this, we can have 1, 2, 3. Okay. I think it's easy to visualize also, right? Okay. Now that's the local maxima and minima of the polynomials. So yeah, I think we could go through. Oh yeah, one additional informations on the polynomials. We could also have what we call the multiplicity. Okay, the multiplicity. So what is multiplicity? Okay, what is multiplicity? Let me give you examples first, and we can go through these definitions. Okay, one more. So let's say we have p of x with power of 4, and this is the functions. Okay, so x power of 4 and x minus 2 with cubes and x plus 1 with square. So what's the deal with this multiplicity? Multiplicity means this part we call the multiplicity. So we will have x 4 times, and we have x minus 2 3 times, x plus 1 2 times. Okay, and this number 4 3 2, it will determine how the graph will be near the intercept. Okay, near the intercept C. Okay. Now here's the deal. So let's draw first. Let's sketch first. Sketch roughly. Okay. And here's I will just going to use to show you how it looks like and what will be the conclusions. Maybe here. Okay. Okay. So we start by looking at the zeros. Okay, so we can start by zero is a zero of, we say, multiplicity 4. Okay, and 2 is a 0 of multiplicity, or let me say multiplicity as m. Okay, m. Multiplicity 3, and negative 1 is a 0 of m 2. Okay, multiplicity, m is multiplicity. Okay, so we are going to see that this 0 has multiplicity 4, and negative 1 is 2. It's called the even multiplicity. Okay, and and 2, this 2 is odd multiplicity. Now if we look at the theorem, if we have the m is odd and m is of course greater than 1, we are going to see that nearby the point C, we will have the graph like this, like that, or like this. Okay, depends on how we sketch the graph. Okay, and if the m is even, we are going to see that it has this or this. Okay, now because this is just an example, so if we look here, okay, so we are going to have 0. Okay, negative 1. Let me write negative 1. Negative 1 is here, 0, and then 2. Okay, negative 1 and 0 has even multiplicity. So we are going to see, and we check all, like usual, we check all the conditions, all the points. We check also the line numbers. Okay, we check the line numbers. We check the negative 1, 0, and 2. We check that this will be negative. It's still negative, and then it goes to still negative going through here, and positive about there. Okay. And what's interesting is, because it has multiplicity, to make this negative make sense, we need to rearrange the curve, right? How it's going to be, or we need to rearrange its directions. So which means when we have this curve, okay, and it goes to the negative 1, and because it has even multiplicity, it need to take some turns at this negative 1, like that, and then it goes back here. And we could also check with some numbers, like for example, we check this negative half, and then after that we get through the 0 again at 0. Okay, we get 0 again, and then at 0 it's also have the even multiplicity, so we will have this kind of graph like that. And of course we can also check the what we have here, if you would like to check, like this, maybe 1 is the negative 4 before we got to x equal 2, which is the another zeros. So this will be going to be there like that, and then it goes back to 2. So instead of going directly like that, because of multiplicity, we are going to take some times and then going there. So for odd multiplicity, how it looks like, the direction, it depends on the whole function. So it could be like this or like this. Okay, so this is another thing that you need to keep in mind, how the multiplicity affect the graph. Okay? Affect the graph, or affect the zeros, or affect the graph near the zeros. Okay, I hope you understand the point. Okay, so that's the multiplicity. Okay, I think that's it. So at least we know how to graph with zeros and with some additional multiplicity, and also we can identify the local maximum and local minimum in polynomial functions. Now, the next sections we are going to move on to the how to define polynomials and maybe rewrite a new functions of polynomials with a more precise and clear terms. Okay, so we could start with the it's called the dividing polynomials. Okay, dividing polynomials. And I think you have learned this before, but let's just review a little bit. It is quite important, especially if you're still taking calculus 1 or calculus 2. This dividing polynomials is one way to rewrite forms, especially for rational functions that has polynomials inside. Okay, that we will have. This dividing polynomials techniques will be really useful for that. Okay, so actually we start like, for example, we divide 38 by 7. We know that this is going to have 5, right? 5 something, and then we have another 3/7, right? And we could take this as plus like that. So the terms, we say this is the divisor, this is dividend. Well, the term is not necessarily important, but what you need to make sure and confirm is how the structure will be. Okay, the terms, maybe one terms or 2 terms is important, but the other part is not really. This is quotient, this is remainder. Perhaps this remainder is important, okay, and it's quotient. The other part, not really. Okay, so as long as you know the structure, it should be okay. Let me give you the basics. Okay, so how to divide. So if p of x and d of x, they are both polynomials with d is not equal 0, so we will have another functions of polynomials when we rewrite this p of x divided by d of x. So we could write down this q of x here and r of x, which is the remainder, okay, and this q is quotient. Okay, so we could write q of x plus r over d, or we could write down p of x equal d of x multiplied with q of x plus r of x. Okay, as long as you know the structure, should be okay. Okay, for example, 6x squared minus 26x plus 12 divided by x minus 4. So we could start with just usual divisions like we learned from the elementary school, I believe. But we need to divide this with x minus 4. Okay, so we how to do that? We start by looking at the highest degree, which is the x squared, and it has 6x squared, so we are going to multiply 6 minus 4 with 6x. Okay, now we multiply this 6x squared minus 24x, and we need to subtract this. Subtract. We are going to have negative 2x plus 12. So negative 2 is in the front now. It's the highest degree now. So we are going to multiply with negative 2. So negative 2x plus 8. Okay. So minus. So we cancel. We cancel. Okay. This will be 4. And we stop here. Now we could write down the terms. Let me write a little bit down here. We could write that this is 6x minus 2 plus 4 over x minus 4. And it seems from the look of it, this part here is much more simplified instead the left part, right? And of course, if you now learning calculus, or if you have learned calculus before, this is a simple way to write functions. And if you could imagine, we need to integrate this will be really easy to be integrated, right? If you remember the calculus. Okay, now let's see the other power. Or we could also write down the 6x squared minus 26x plus 12 is x minus 4, 6x minus 2 plus 4. We could also rewrite as this. Okay, let's see another example, and then we move on to another perspective or another method. So let p of x is 8x4 plus 6x squared minus 3x plus 1, and dx is 2x squared minus x plus 2. So we need to divide this p of x with d of x. So let's start with maybe right here, or maybe here, at x4 and divide with this. And remember, we start from the biggest one, the highest degree. So 8x4, so we have 4 and then x squared. So we need to make it the same. So 4x squared multiply, and then 4x squared multiply with negative x, negative 4x cubed, and then plus 8x squared. Okay, now this is also something that can happen. We have x cubed, but we don't have here, so we imagine that at here we have 0x cubed. Okay, so you need to be careful. So canceling this, and then we have 0 minus 4x cubed. It goes to be 4x cubed, and then 6x squared minus 8x squared minus 2x squared minus 3x plus 1. Okay, and then now we have 4x cubed, so we need to multiply with plus 2x, so we will have 4x cubed, and then negative 2x squared, and then plus 4x. Okay, and then we need to subtract. Cancel this, and also cancel this part, and we have negative 7x plus 1. It's already lower than what we have for dividing, so we stop here. So we could write p of x over d of x is equal to 4x squared plus 2x minus 7x plus 1 over 2x squared minus x plus 2. Or we could write completely multiply with that. So 4x squared plus 2x multiply with 2x squared minus x plus 2 minus 7x plus 1. Or maybe let me write with clear like that. To make sure that we are on the same page. Okay, that's we called the long division. So this method is called the long divisions. Long division in polynomial. Okay, this is what we call. We have another method as well. We call the other method as synthetic division. Okay, this synthetic division is works when the divisor is in the form of x minus c. Okay, the one that we need to define. Okay, we need to divide with what, so that what is x minus c, which means it can be x plus 4, x minus 1, x plus 3, blah blah blah. Okay, but when we have like the form is in the quadratic form, then we cannot make our synthetic divisions. Okay, so for example, we take 2x squared minus x minus 3. We need to divide this, divide with x minus 3. Okay, let's say that's our problem. So we start with maybe take different case, x cubed. Yeah, I wrote the solutions instead of the equation, sorry. Okay, so we start with the x squared, 2x squared, so 2x cubed minus 6x squared, right? Okay, and we have negative x squared plus 5. Okay, and then we need to multiply with negative x. So maybe to make it more clear, let me give you just slide maybe with more. So it has 0 at that point, just to make sure that we are clear. So we have negative 3x plus 5, and then we have negative 3, and we have negative 4. So the remainder is 4, negative 4, sorry. This is remainder. This is the quotient. Okay. Now the synthetic divisions, let's see the structure of the function that we are going to define. So 2x cubed minus 7x squared plus 5. Okay. Now notice the coefficients in all the terms. But to make this synthetic division works, we need to include the terms that's supposed to be there, but the coefficient is 0. For example, the x. So this is constant here. So it actually has x, but its coefficient is 0, right? Okay, it's actually like that. So the synthetic division works with, we write all the coefficient 2, negative 7, 0, and 5. Okay. And then we take this like a line like that, or maybe line a little bit down there, and then x minus 3 we could write as 3. So because we write 3, we are going to add, not a subtract. So let me just give you these techniques first, okay? And then we can have some repetitions. So we start with taking down this 2, going down here, and then this 2 multiplied with 3, it's 6, right? So write 6 here, and then add. Negative 7 plus 6 is negative 1. And then again, we multiply negative 1 to 3. It's negative 3. We wrote here and then add. And then same thing, we multiply with negative, we multiply negative 3 with 3, which is negative 9. It's become negative 4. Okay, now this is the remainder, and this will be the quotient. So 2x squared minus x minus 3. Okay, so notice that we have the same conclusions. Okay? And for the syntactic divisions, it's more simplified, it's more clear. We are only consider the coefficient from the polynomials, and we can do the divisions more, I think, more easy. Okay. All right. Now one more thing about this remainder things here. When we divide and we divide completely, there is no remainder, right? The remainder is 0, which means the division is complete. Okay, but if we have the remainder, it means that it's not really completely divided. Okay, so let me write here the remainder theorem, and it is actually quite useful as well. So if polynomial p of x is divided by x minus c, then the remainder is the value of p of c. We could imagine from this part here, when we take p of 3, it means that we are going to have this. Let's just take this inside. 3 with power of 3 is 27. It's 54. It's 56 plus 5. So we are going to have, oh, sorry, I'm wrongly calculated. 9, 7 is 63. So we have what? Negative 9 plus 5 is negative 4. Also the same, right? The same remainder. So this is the remainder. Okay. Okay. And you know, if c is 0, well, it's not the theorem, but let me just write additional information. If c is 0, if c is zeros, which means that when p of c becomes 0, so it means that this is 0 remainder. So if you have some number here, that is your remainder. Okay, but if it becomes 0, it means there is no remainder. So we have completely divided the polynomials with the c. Okay, that's the remainder theorem. I think we are going to have more examples later on. So this is, I think, a new way, syntactic divisions and remainder theorem to help at least observe and identify the polynomials. Okay. Okay, now we are going to move to the new sections, which is the real zeros, or red with black. So real zeros of polynomials. So we are going to describe in more general. Okay. Okay, consider polynomial and if we write in the expansion form, if you multiply all of this, we get this. Okay, and we know from this factors we get the zeros of p are x equal 2, x equal 3, and x equal -4, okay? And we see that these numbers, and when we compare with what we have in the P, let's say we are going to look at this 24, okay? Because this 24 is the result of multiplying and addition and adding all the components on at least if you see this -2, -3, and 4 is going to be multiplied, and it's become 24, right? So if we take sometimes and try to reverse, okay, so if we are given this this P, the expanded form of P, this 24 is obtained, right, from -2 multiply with -3 and multiply with 4, okay? And we know that this will be 24. So we could have some, at least going to have like a theorem on how we can get a possibility of zeros from the constants, okay? Now let me write the theorem, and maybe I'm just giving you the theorem and we can see what it is. So if the polynomials, this, okay, the general form of polynomial, and they have all coefficients. Now if we have a rational zero of P is P over Q, which P and Q is actually a factor of the, so P is A0, which means the constant, and Q is the leading term, if you remember. The leading term is on the front, usually it's the highest degree, that has the highest degree. So we are going to have the form is P over Q. This P over Q is actually, we can say that it is a possibility of zeros. Okay, so we can have a possibility from the factor of the constant. Like when we imagine like the 24 is comes up from, at least we can say plus minus 1 and plus minus 24, okay, if we take the factor. And we can also say 2 and 12, both for positive, negative, because that's also a possibility, right? Because have negative, negative, or positive, positive, okay? And then we can have also 3, right? And we can also have 4 and 6. And since the leading term is only have 1, so we only concern on the Q. Oh, we only concern of the P, sorry, P. So all these numbers will be candidates for zeros, okay? So let's see another examples to make sure that we understand what it is. So we have P of x. Okay, so we see that this is P, this is P, this is Q. Okay, so we can take this, that 2 can be right as these two factors. So we could test, the first thing and we can do is we test. We take 1 and it's 0, okay, so it's our zeros. We can take the -1 and this will be 4, right? So 2 plus 2 for 4. We take 2 4 and then -2, and this is 0, and we know that this is going to be the zeros. Okay, so this is zeros. Okay. Okay, now another example. Okay. So we get the 6 and 2. So this is P, this is Q. So factor of 6 divided by factor of 2. So we are going to list several numbers, which is plus minus 1, this is plus minus 1, plus minus 2, plus minus 2, plus minus 3, and plus minus 6. That's the factor of 6. So we will have possible rational zeros. This will be plus minus 1, plus minus, so we are going to take so this is 1, okay, this is 2, and we can also have 1 over 2, 3 over 2, 3, okay, and 6. Okay, now we take plus minus 2, plus minus 3, plus minus 6, and then the rational one, half and 3 over 2. Now, well, we need to take all of this as our testing, but how we test our zeros? Well, we could take this and then compute, but let me give you a method. Okay, we can actually use the synthetic divisions. Okay, so we can write this is 2x cubed so 2, 1, and then divide with the, let's say we take the x minus 1, so we take x equal 1. So we have a remainder here, so not zeros. We can also check the other one, -1. Well, this is also not good. This is a remainder, so not zeros. So maybe you take 2. This is zeros. So this is zeros. Okay, after we get this is zeros, which means we can make this as a 0. So we could take the result of the quotient, which is 2x squared plus 5x minus 3. So we will have these equations. Okay, now maybe if we take this as our another polynomials, and we can do the synthetic divisions, or if we could take, maybe we could take factorization. So let's do that. So 2x and x, so maybe 3 and -1. So this will be negative 6x minus 1, it's plus 5. So I think this is okay. So we have x minus 2, 2x minus 1, and x plus 3. So our zeros, x equal 2, x equal half, and x equal negative 3. Okay. So all the long division or synthetic divisions will be really, really useful here to check the whether it has remainder or not. Okay, to determine the zeros or not. Okay. Okay. Okay, maybe we could take the okay, let's say we have another example. Okay, so find zeros and maybe sketch P. So first we take this is P and Q. So possibility of zeros. So plus minus 1, plus minus 2, plus minus 5, plus minus 10. And plus minus 1. So all this will be our choices. So we could take the synthetic divisions. So first, maybe try 1. Its remainder has a half a remainder. Well, we could maybe just erase this and maybe try 2. Okay, we still have remainder. Well, let's say 5. So it's zeros. So 5 is zeros. So we could take this x cubed, negative 5x plus 2, and x minus 5. This is the equations. So we also can take this into synthetic. So 1, 2 or 1, so let's say 2. Well, we have a remainder for 2, but maybe negative 2. So this will be 1, negative 2. Oh, wait. Oh, it should be. Wait. I think I made a mistake here. Let me check. This is supposed to be negative. Okay, sorry. It's supposed to be negative. So this will be 0. So negative 2 also zeros. So x minus 5, x plus 2. Okay, this is the equations now. Can we factorize this? I don't think we can factorize this, right? So, well, we could take the okay, I think this is the equations. So if we take this equaling this to 0, so we will have is plus minus square root of 2, so x is 1 plus minus square root of 2. Or if you would like, you can always go to the your favorite, probably the ABC formulations. Sorry. Okay, we can also use this, and we will get the same result of this from there. So zeros, okay, zeros. X equal 5, x equal negative 2, 1, x equal 1 plus square root of 2, and x 1 minus square root of 2. So we have 4 zeros. So this is also possible combinations. And of course, we could take the these zeros into a line number. So negative 2, 5. Well, 1 plus square root of 2 is around 2 point something. So let me maybe 2 point something here. This is supposed to be for x 1 plus square root of 2, and let's say 0 point something is for the 1 minus square root of 2. This is for minus. Okay. So we could take the let me write here. It's positive. So negative, positive. This is positive, so it should be negative. And then between this, we could take 0. Take 0 is negative, positive is negative. So we'll have positive. And then maybe from this point, we could take 3, x equal 3. Sorry. 3 is negative, positive, positive. So it should be negative. And after that, we take 6, it's supposed to be positive. So we will have well, we have crossing here, and we should crossing also near 0, maybe here. Okay, so we could also check the point if you want some point. You can check also. Okay. Okay, we going to continue. The next part is the card. Not this. The cards rule of signs. So what is the card rule of signs? So René Descartes is one of the famous philosophers and mathematicians that found one way to eliminate candidates. Remember that we have, if you remember that we have px, and maybe let's say we have ax squared plus bx plus c. Well, we could take maybe cube and then square. Let's say we have like cubic expressions. Remember that we have p over q, so from here and from here. So we take, let's say it's p q, so p over q is our possible of the rational zeros, right? Rational zeros, let's say candidates. Okay, so the card rule of signs will take this p over q and eliminate some of them and making some rules to make sure, and then confirming what kind of zeros we are going to have. Okay, so let me just tell you the story of this Descartes, the formulations. Let me take this. Okay. So let P be a polynomial with a real coefficient, so it can be any polynomial. So first, it says that the number of positive real zeros, okay, so the zeros is positive, is either equal to the number of variation in signs in P of x, or is less than that by an even whole number. I will explain later what does this even whole number means. But the second one, for negative real zeros, is equal to the number of the variations in sign in P of negative x, or is less than that by an even whole number, same thing. Okay. So what we are going to do with this? Okay, so I think it's better to give example directly what the variation in sign means. Okay, so let's say we have a P of x. Okay, let's say we have this. Okay. Now, using the Descartes rule, what we are going to find is the variations in sign. So need to find variation in sign in P of x. Okay, so what does it mean is we are going to see this is positive, right? Positive, still the same, positive, positive, okay? Nothing wrong with that. And then positive, this is still positive, but then we take this and it's become negative. So one change, right? One change. So there's only one change, okay? One change. So we have one variations of sign. So we have 1 positive 0. Okay, and now we take p of negative x. So we need to change this equation for 1. So 3x with power of 6, because it's even number, so it's still the same. And this will be negative 4 because it's an odd number for the degree, odd degree. And then negative 3x cubed, and then this is going to be plus x, and then minus 3. Okay, now we have, this is positive, become negative, so one sign change. Okay, one sign change. And then we also have this, and we also have this. We have 3, 2, 3. So three variation of sign. So what does this mean? So one variation of sign for the first one, it has 1 positive 0. But what does it mean if we have 3 variation of signs? This means we are going to have px has either 3 or 1 negative zeros. Okay, so let's try more examples. Okay, let's say we have these functions, and then find possibility on how many positive or negative real zeros these functions have. And the second question is determine the real zeros. So finding the possibility means that we are going to use the Descartes rule. So Descartes rule. So we are going to check using the first is the f of x. So we are going to see the change in the signs. We'll have this. Okay, so 1 and 2. Okay. So means that f of x have positive zeros or 2 positive zeros or 0 or nothing for the positive zeros. Okay. So that's the meaning. Okay, that's the meaning. If you remember the definitions. So the number of let me make it clear. The number of positive real zeros is either equal to the number of variation in signs or less than that by an even whole number. So you need to minus 2, minus 2, minus. So if you have 5 or if you have 4, you need to minus 2. So you can become 2, minus 2 becomes 0. So you have 4 or 2 or 0. That's also the same thing here. It's 0, 2 positive zeros or 0. Okay. Okay. This is the first one. So the second one, we check the negative x. Okay. So we get that this is only having 1. Okay. So 1. So f of x. So if it is just 1, we cannot minus 2 because it doesn't really help anything. Okay. So it has 1 negative zeros. Okay. We could take this into our table. So we have positive, okay, we have negative, and actually we can have our imaginary number. Okay. So we have a total, okay, total zeros. because we have the cube, so we are going to expect that the total will be 3. So if we have 2 or zeros, and the negative 0 is 1 for all possibilities, so this will be 1, 1. The total should be 3. So the first one, it has 0 imaginary number, but the second one, it has 2. So we can have 2 conditions. We can have 1, we can have 2, but we need to make sure which one is our path, okay, which one is our structure. Okay. Okay, so this is for number A. This is for number A. So we could stop on for number A, and number B is finding the real zeros. Okay, let's say we start with from here, from P over Q. Okay. We could take the synthetic division. We could take trial and error from these numbers. We could take 1. We have zeros. Okay, we could take another one. Or we could take from here. So we will have x minus 1, x squared minus x minus 2. Now this can be, I think, can be factorized. X minus 2 and x plus 1. Okay, so I think we could have x minus 1, x minus 2, x plus 1, which we can take this as zeros, as x equal 1, x equal 2, and x equal negative 1. So we have 2 positive zeros and 1 negative 0. And it's completely perfect with our path number 1. So this is our path for the Descartes rule to be true. Okay. Okay. Well, we could take another examples if you would like to know more. Okay. So let's say we have another functions. Let's take functions x cubed minus 6x squared plus 13x minus 10. Okay. Okay, now how many possible root? Okay, so how many possible root for all possible zeros? So first we could take the equation and count the sign change. Okay. So we have 1 here, 2, 3. So we have 3 positive zeros or 1 positive zeros. Okay. And then take f of negative x. So we have negative x cubed. We have this change, right? 1 and then 2. Oh, wait. Should be having a squared, sorry. Squared here. Squared. Okay, this is supposed to be different. So negative x, so negative 6x squared. Oh, so all negative, so 0. So 0, negative zeros. And then same way, we take a table. So we have 3 or 1. And this is both are zeros because not they don't have possibility on having the negative zeros. And since it's the cube, so we have 3. So we have 2 roots. Okay, 2 roots. But which one is the one that is going to be true? Well, it's not the, well, if you answer up until here, it's already correct. But if you want to make sure that you get the final answer, we could write down the possibility. So first we could see from the equations x cubed. So from this 10, we could take the p over q is plus minus 1, plus minus 2, plus minus 5, and plus minus 10. So we could start from checking syntactic divisions. So checking 1. And I think it's not completely divided, so not zeros. And maybe 2. I think we get 1. Okay, we get 0. So this is zeros. And we can write down the formulations for the polynomials. Okay, now can we factorize this further? Can we factorize 1, 5? It's supposed to be 5 like that, but well, it's not possible to be calculated. We could take this, try the quadratic formula from this formulation that I believe you're already familiar with. Okay, we could take that, or we could take into a complete square. So this is supposed to be 4, right? So this is minus 4. So x minus 2 squared minus 4. Oh, not minus 4, sorry. Minus 1. Oh, plus. Sorry. Okay, now this is your equations, and we can solve this. It's negative 1. So what's happened here? What's happened is we are going to have our imaginary number, which is definition of the imaginary number is plus minus of, or square root of negative 1 is the imaginary number. Okay. So the true path for our solution is this one. So we will have, so f of x have 1 positive 0 and 2 imaginary zeros.